hypotenuse.
I'll be explaining the theory behind circular motion, and there'll probably be a second part to this video for practice questions and stuff like that. Yeah, so if you've got a particle P traveling in a circular path around the origin at a constant speed, it will still be accelerating, even though it has a constant speed. The reason why it's accelerating is because it has a velocity, and velocity is a vector product. It's a vector quantity, sorry. That means it has both magnitude and direction. And as P makes its way around a circle, it will change direction. And since acceleration is defined as the rate of change in velocity, and there's a change in velocity, that means there's an acceleration. Now, if we use the equation for our resultant force, F is equal to ma, if there's an acceleration there, we know that it's going to be a resultant force. So this resultant force actually has a name, which is called the centripetal force. And the centripetal force is the force that makes a body follow a curved path, and it's always directed towards the center. So the centripetal force is a resultant force that always acts towards the center. There's a few equations for circular motion that you need to know. I'll show it to you, I'm not going to derive it. Acceleration is equal to velocity squared over radius. Acceleration is equal to omega squared times radius, where omega is actually the angular velocity. Angular velocity refers to how fast a point object revolves about a fixed origin. So as you can see in the diagram, this is our angular velocity. Now if you equate these two accelerations together, we get v is equal to angular velocity times the radius. And we also can plug any of these accelerations into our resultant force equation to get F is equal to mv squared over r, which is equal to m omega squared r. So these are the equations that you'll basically use for circular motion. Moving on to the different scenarios. So you can have friction, a car going around a circular path. Friction will act towards the center. So friction is our centripetal force in this case. If you've got a string and an object at the end of the string, and if it's spun in a horizontal path, tension will be our centripetal force because it's acting towards the center. But if the string is spun in a vertical path, right, our tension, our resultant force will not only be the tension, but there'll be a component of weight. I'll go over this later on because this comes up later on as well. And the next one is gravitational force and the satellite going towards Earth, but you don't do that much in Furthermaths really. Another case could be a banked track for professional cyclists. Since there's little to no friction with these bikes, there's no friction going towards the center. So you may be wondering, what will be the centripetal force? Well, there is a normal contact force, or also known as the reaction force, which acts at right angles to the surface. Right. So at right angles to the surface is showed by N, the normal contact force. Right. And since the normal contact force is going at an angle, there'll be a horizontal and vertical component of this normal contact force, right? So the horizontal component will act towards the center, and this will give us our resultant force. And you can see our horizontal component will be n sine theta. Okay, the next part, another thing is the Ferris wheel. So at the Ferris wheel, there's going to be a resultant force acting towards the center, right? However, if you're a person in the Ferris wheel, right, there's a weight going down, mg, and there has to be a normal reaction force going upwards. Right, so there has to be a normal reaction force going upwards. And if we want at the bottom, right, at the bottom of the Ferris wheel, the normal reaction force will be greater than weight because the force has to go towards towards the center. So at the bottom, normal reaction will be greater than weight, as they're going opposite directions, so must be greater to be able to go towards the center. Whereas at the top of the Ferris wheel, right, we have weight already going towards the center, so reaction force will be very little. Right, so at the top of the Ferris wheel, our weight would be greater than our normal reaction force. Now moving on to chronicle pendulums. So this is a chronicle pendulum. It's basically when it's set up like this, and it's going in a horizontal circular path, but the string is not also in the horizontal path. So our tension will no longer be the resultant force, because as we know, the centripetal force acts towards the center. Right? So we got an angle here. So if we use trigonometry to find our opposite side of the triangle here, we will get ft sine theta will equal to our resultant force, right? Because the centripetal force acting towards the center. We've also got another equation that we can use. Because it's an equilibrium, right? It's only going in that horizontal path. Our vertical forces must cancel out. So our vertical force of tension will be Ft cos theta, and that must be equal to the weight. Many times in many questions, you'll have to do simultaneous equations of these two, right? So you need to split it into horizontal and vertical, okay? The next bit is circular motion 2. So say you got an object at point A. If we raise that object to point B, we're providing work onto the object, so the object gains potential energy. Once at point B, we release the object, and the object will begin to accelerate towards the center, as potential energy will be converted into kinetic energy, right, to point A. So once it falls to point A, assuming that at point A it's at equilibrium position, so there's no height in point A, we'll reach maximum kinetic energy, right? And then from point A to point C, our kinetic energy will be transferred into gravitational potential energy. So from A to C, kinetic energy will be transferred to gravitational potential energy. And then at point C, the object will reach its maximum height. Once it reaches its maximum height, the velocity will be 0, because the object will begin to start changing in directions, going towards A. So that's why at point C, at maximum height, we have only gravitational potential energy, right? And basically this is conservation of energy, where no energy can be created or destroyed and it's only transferred. Now on to some more problem-solving questions. This one will require both conservation of energy and forces. So we'll go through it. A smooth solid sphere with a radius of 4 meters and a center of O is resting on a horizontal table with its flat face in contact with the table. A particle P of a mass 5 kilograms is resting on a hemisphere when it starts to slip from rest at the highest point at point A on the hemisphere. If the hemisphere stays in a fixed position, find an expression for the normal reaction force of the particle to the surface of the hemisphere when the angle between OP and OA is theta. So we want to find an equation for the angle. So first we're going to use conservation of energy, right? So we know that the gravitational at point A, right, the gravitational potential energy plus the kinetic energy must be equal to the gravitational potential energy plus the kinetic energy in point P, right? So we can start calculating this. So it's given that at point A, it's at rest. This means there'll be no velocity, so there'll be no kinetic energy at point A. So we only have GPE is equal to GPE plus KE. So we know that GPE would be the radius times mass times gravity is equal to, and the radius at point P, right? The height of point P will no longer be its radius. As you can see, it would be, if you use trigonometry, it would be r cos theta as our height, right? Because you've got a radius here, the angle will be over here, so r cos theta be our height times mass times gravity plus 1/2 mv squared. Now, as you can see, we've got a common factor of mass, so we can cancel all that out. We get Rg is equal to Rg cos theta plus r half v squared. We can rearrange this to make it equal to v squared. So v squared is equal to 2 Rg 1 minus cos theta. So now we got to find an equation to get rid of our velocity squared, because you only want to find the angle. So next we can use forces. So at point P, we'll have a resultant force, right? And the resultant force will be equal to the component of weight going in the direction of resultant force, right? So you've got weight going downwards. We have weight going downwards, right? mg. The angle here, we want to find the component of weight going towards the center. So again, we can have mg cos theta that go towards the center, and I'll be subtracting the reaction force. As I said before, that the reaction force acts at right angles to the surface. So our reaction force will go in this direction. So it's opposite direction to the weight. We can subtract the reaction force. Okay. And now we know our resultant force is equal to mv squared over r. And then we can rearrange the equation. Now we can rearrange our equation to make it equal to r, our reaction force. We've got reaction force is equal to now that we've got two equations, we can plug in our v squared over here with our v squared in the reaction force, because we're trying to find the equation for the reaction force. So we've got r is equal to m 2 rg 1 minus cos over r minus. So, and our r will cancel out. So our equation of our reaction force will be equal to 2 mg 1 minus cos theta subtracted by mg cos theta. And that's the equation.